In the previous class, we have seen an introduction to third module. We have seen what is source coding theorem, and we have seen the basics of what is meant by sampling. Am I right? Hope all. Okay, in today's session, we'll be studying sampling. So basically all signals, whatever is generated is of analog signals. All signals, whatever is generated is naturally a analog signal and it has a continuous value in time. So what is meant by digital communication? Why do you want to digitize a system? What are the advantages of digital communication over analog communication? So what it means is that any kind of signal, whether it is a signal, whether it is a message signal, say for example, a radio jockey is speaking from one end, or a singer is singing a song from one end, you want to listen to the song, it is being broadcasted through some electronic media and it is being received at the receiver's end. So you can never imagine a digital signal directly being transmitted. The singer's song, whatever the song it is converted into an electric form, and in that electric form, it would look like an analog signal only. It has a continuous value over time. Okay. So what is meant by sampling? Definition of sampling in general. Sampling is breaking up of the signals, breaking up the time continuity of the signals with the probability of regeneration. This means that sampling is something in which we are going to avoid all the redundant parts of a signal in such a way that we are able to reconstruct the signal, the original signal, by the dots that is available, right? Instead of sending a line, if we wanted to send a line, if this is the signal, if you could send it in terms of small samples, this particular signal can be regenerated at the other end. This process of eliminating the spaces here is called as sampling. In the previous class, I told you that waveform encoding means sampling, quantization, and encoding. I hope all of you remember that, right? The last class we have dealt in detail about waveform encoding, in which I told you that waveform encoding consists of three parts. The first part is sampling, second one is quantization, and the third one is encoding. So first thing what we have done is that we have broken the continuity of the signal and we have made the signal discrete. Okay, so we have digitized the signal, but we did not digitize it completely because we have not analyzed values for that. So if you listen to me very carefully, only then you will understand what is quantization, and it is very important and it is very commonly asked question wherever you go. Whether it is for an interview or a viva voce, you may need to explain what is meant by quantization. Only sampling nobody is going to ask you because they are expecting that you can know it. It's a very easy concept, but quantization is not that easy. See, listen here. This is a sinusoidal signal or this is some message signal. What I have done is that I have sampled the signal. That means I have removed certain, I've made the signal like this, right? The original signal was continuous. I broke the signal and I made it discrete, and I made discrete points here. Okay, I made discrete points here. Now quantization means I am assigning a value to each of these points here. This value is a set of binary digits and it is called as a symbol. I am dividing this particular y-axis completely, say into 3 or 4 or number of levels, different levels. Let me call it as, let me divide this into 8 levels. All levels are 2 raised to n levels because I am using zeros and ones to mark these points. Okay. So let me consider this. I am dividing this into 4 points, for example. 1, 2, 3, and one more point you can use here. Let me denote this point by 0, 0. Let me denote this point by 0, 1. Okay. Let me denote this point by 1, 1, for example. And let me denote this point by 1, 0, for example. We have 4 values. So once I have made this into discrete, I can assign a value which is closest to this for this particular point. Okay. So the point here, let me call this as A. A will be denoted by a symbol which consists of zeros, 0 and 1, 2 bits, right? And this is a symbol and I need to transmit 0, 1 instead of A. That is how I am quantizing a signal. Now I can make it as 8. 2 raised to n means if 2 raised to 2 it is 4. 2 raised to 3 means 8. So I can give here 3 symbols, 3 bits to make a symbol. So a symbol can consist of n bits. Okay, n is a value where you are going to break your signal into so much number of levels. So in level 2, that is L is equal to 2, we have 4 values. If L is equal to 3, that is L is equal to 8 and N is equal to 3, we have 8 breakups and 3 bits per symbol. This is how we are quantizing a signal. Is there anybody in this class who did not understand what is meant by quantization? What are different quantization levels? How to quantize a signal? All of you understood? Everybody understood? This is quantization. So three steps of digitizing a signal, converting an analog signal to digital signal. In the first part, we have sampled the signal. In second part, we have quantized the signal. Quantized the signal means converting that particular point into symbols. Right? Yes or no? All of you understood? Is there anybody in this class who did not understand what is meant by quantization? No. So whatever I've explained to you now, I've given it in terms of words. The process of digitizing the domain is called sampling, and the process of digitizing the range is called as quantization. That is why this signal obtained after quantization is called as discrete time, discrete valued signal. That means you can consider quantization to be done in the frequency domain, sampling in case of frequency domain. The third thing is called as encoding. Encoding is a representation of the defined set of values of finite number of probable time and voltage current values. The symbols that is obtained after quantization is further encoded, compressed. This process is called as encoding. You have different types of encoding techniques. We won't be studying in detail about encoding techniques now, but you have this in your practicals in the coming semesters. Now we'll study how to create a sampled signal. When you multiply a signal with a zero, what happens? That signal gets cancelled, right? The same principle you can utilize it here. You can multiply with a delta function, unit impulse function. When you multiply a signal with a delta function, what happens is that the signal gets sampled and broken down into discrete values, right? So this is the simplest and the oldest method of sampling a signal. So in that case, S of t is given by minus infinity to infinity delta nts, where this nts and ts stands for the sampling time. Now let us consider the Fourier transform of the sampled signal, sampled waveform, ms of t. Since ms of t is the product of mt and s of t, the Fourier transform of ms of t is the convolution of Fourier transform of m of t and s of t. Whatever we are doing in time domain, we are converting it into a frequency domain. So the impulse signal 1 by Ts will be representing S of S as 1 by Ts, n is equal to minus infinity to infinity delta F minus n Fs. That is the Fourier transform of S of t. Convolution with the impulse will give you the sampled signal. Now let's draw the waveforms. Now let's draw the waveforms for whatever we have studied so far in both frequency domain and time domain. In time domain, the message signal looks like this. This signal in frequency domain, it is like this. And this is how you get it converted into. So this is sampling and quantization will give you this one. So this is the equation for sample signal.